Hello students, let's continue our chapter 2 solutions. First let's recall what is Henry's law. This law states that the partial pressure of a gas in the vapor phase is proportional to the mole fraction of the gas in solution. It is expressed as partial pressure P, it is directly proportional to mole fraction chi. That is, P is equal to Kh into chi, where Kh is the proportionality constant known as Henry's law constant. So this is the mathematical expression for Henry's law, that is P is equal to Kh into chi. Next we will see the graphical representation of Henry's law. In the graphical representation of Henry's law, partial pressure is taken along the y-axis and mole fraction is taken along the x-axis. So when we plot partial pressure versus mole fraction, see we get a graph like this. That is, we get a straight line graph. Okay, that means partial pressure varies linearly with mole fraction. That is, as the partial pressure increases, mole fraction also increases or vice versa. Next, we will see the relation between Kh and solubility. That is, Kh means Henry's law constant and solubility. Now, as the value of Kh increases, the solubility decreases, or as the value of Kh decreases, the solubility increases. That is, Kh and solubility, they are inversely related. Next, we will see the relation between Kh temperature and solubility. For this, we have a tabular column, and in this tabular column, we have three columns. First column is gas, second for temperature, and third for Kh. That is Henry's law constant. Now, first we will start with nitrogen gas. Nitrogen gas at 293 Kelvin, it has a Kh value of 76.48. Nitrogen gas at 303 Kelvin, it has a pH value of 88.84. That means as the temperature is increasing, the Kh value is increasing. Next, we will move on to oxygen gas. Oxygen gas at 293 Kelvin, it has a Kh value of 34.86. And oxygen gas at 303 Kelvin has a Kh value of 46.82. That means as the temperature is increasing, both for nitrogen as well as for oxygen, the Kh value is increasing. Now, see, you can see that as the temperature increases, the Kh value for nitrogen and oxygen is increasing. Next, as the Kh value increases, the solubility decreases. From our previous relation, we know as the Kh value increases, the solubility decreases. So, we can say that as the temperature is increasing, the Kh value is increasing, and so the solubility is decreasing. Likewise, as the temperature is decreasing, the Kh value is also decreasing, but as the Kh value decreases, the solubility increases. That means, see, it is due to this particular reason that aquatic animals are more comfortable in cold water. That is, in the cold water, the temperature is less. So, if the temperature is less, the solubility will be more. So, as the temperature is less in cold water, the solubility of oxygen will be more. And so, aquatic animals will be more comfortable in cold water rather than in warm water. Next, we move on to the effect of temperature on the solubility of a gas in a liquid. So, as the temperature increases, the solubility of a gas in a liquid decreases. Here for an exothermic and endothermic reaction. Exothermic reaction is a reaction which liberates heat energy. For an exothermic reaction, the solubility decreases with the increase in temperature. Whereas for an endothermic reaction, that is, endothermic reaction is a reaction which absorbs heat energy. For an endothermic reaction, solubility increases with the increase in temperature. So this is the effect of temperature on the solubility of a gas in a liquid. Next, we will see the application of Henry's law. Henry's law has got three important applications. First one, it is used in the manufacture of soft drinks and soda water. That is, carbon dioxide gas is passed at very high pressure in order to increase its solubility. In soda water as well as in soft drinks, it contains carbon dioxide. In order to dissolve this carbon dioxide, very high pressure is applied. When you apply high pressure, the solubility of carbon dioxide increases, and this is an application of Henry's law. Second, we move on to the second application, that is, it is used in deep sea diving. That is, in deep sea, as we move down, the pressure is higher than at the surface of the water. When the diver is moving down deep into the sea, the pressure increases, and as the pressure increases, the solubility of nitrogen gas in the bloodstream increases. As a result, more amount of nitrogen gas will be present in the bloodstream of the diver. Now, when the diver tries to come back rapidly towards the surface of water, the pressure decreases. Suddenly, the pressure decreases, and all the dissolved nitrogen present in the bloodstream, it tries to come back and it will form bubbles in the veins, and this condition is known as bends. Hence, divers use oxygen gas diluted with helium gas. So this is the second application of Henry's law. Now moving on to the third application, that is at high altitudes. The partial pressure of oxygen, it is less than at the ground level. As we move up, what happens is that the partial pressure of oxygen is less than at the ground level. This leads to low concentration of oxygen gas in the blood as well as in the tissues of mountain climbers as well as people living in the high altitude region. So since the amount of oxygen that is present in the bloodstream of people living in this area is very less, so it leads to a condition known as anoxia. So these are the three important applications of Henry's law. Next, we move on to the next concept, that is vapor pressure of liquid solutions. Here, we consider only binary solutions containing two components. Liquid solutions, we have already learned what is a liquid solution. Liquid solution is a solution in which solvent is in the liquid state. So here we are considering two types of liquid solution. First one, liquid in liquid. Liquid in liquid means solute is in the liquid state as well as solvent is in the liquid state. That is liquid in liquid. Second, we will study about solid in liquid. That is, the solute is in the solid state and solvent in the liquid state. First, let's discuss about the vapor pressure of liquid-liquid solutions. Now, for that, we are considering a binary solution. Binary solution containing two volatile liquids, and we will denote this components as component 1 and component 2. So we are taking this binary solution of two volatile liquids. Volatile liquid means that liquid will easily vaporize and it will escape into the vapor phase. So we are taking this two volatile liquid in a closed vessel, so that the vapor, that is once the volatile liquid escape into the vapor phase, the vapor will not escape out of the container. So we are taking this two volatile liquid in a closed vessel, and what happens is that from the liquid phase, both the components, it will escape into the vapor phase, and finally an equilibrium will be established between the vapor phase as well as the liquid phase. Let the vapor pressure at this stage be P total. That is, the volatile liquid will escape into the vapor phase and it will exert a pressure, and that pressure is called the total vapor pressure, and the total vapor pressure is denoted by P total. And P1 is the partial pressure of component 1 and P2 is the partial pressure of component 2. Let Chi1 and Chi2 be the mole fractions of components 1 and 2 respectively. Chi1 and Chi2 mole fraction of components 1 and 2 respectively. Raoult's law. So the relationship between the partial pressure and mole fraction was given by Raoult. He is a French chemist, and that law is known as Raoult's law. It states that for a solution of volatile liquids, the partial vapor pressure of each component of the solution, it is directly proportional to the mole fraction present in the solution. So here for component 1, binary solution contains two components. So that is component 1 and component 2. So for component 1, we can write Raoult's law like this. Partial pressure of component 1, that is P1, is directly proportional to Chi1. Chi1 is the mole fraction of component 1. Now, the proportionality sign is replaced by a constant, that is P1 is equal to P10 into Chi1, where P10 is the vapor pressure of the pure component 1 at the same temperature. Next, we will we can write the Raoult's law for component 2, that is P2 is directly proportional to Chi2, where Chi2 is the mole fraction of component 2, and P2 is the partial pressure of component 2. Now, we can replace the proportionality sign with another constant. P2 is equal to P20 into chi2, where P20 is the vapor pressure of the pure component 2 at the same temperature. So, this is the mathematical expression for Raoult's law, and the statement of Raoult's law is very important. Next, we move on to Dalton's law of partial pressures. It states that the total pressure is denoted by P total. So total pressure over the solution phase in the container, it will be the sum of the partial pressures of the components of the solution. So we can express this Dalton's law of partial pressure like this. P total, that is the total vapor pressure, is equal to sum of the partial pressures of the components. Which are the components? Component 1 and 2. So P total is equal to P1 plus P2. Now here in this equation we are going to apply Raoult's law. According to Raoult's law, we know P1 is equal to P10 into chi1 and P2 is equal to P20 into chi2. So we are going to substitute that in this equation. So P total is equal to P10 into chi1 plus P20 into chi2. Now already we have learned another relation, that is chi1 plus chi2, that is the sum of the mole fractions of all the components, that is equal to unity. That is chi1 plus chi2 is equal to 1. Now from this equation we can write like this. Chi1 is equal to, see we are going to get the value of chi1 from this equation, that is chi1 is equal to 1 minus chi2. Now, we are going to apply this value for chi1 in the above equation. So, now our equation becomes P total is equal to P10 into, instead of chi1, we are going to write 1 minus chi2 plus P20 into chi2. Now, we are going to multiply, in the next step, we are going to multiply this. So, P total is equal to P10 minus P10 into chi2 plus P20 into chi2. Now, what is common in these two terms? That is chi2 is common in these two terms. We can take chi2 out, and so our new equation will be P total is equal to P10 plus chi2 into P20 minus P10. So this is our final P total equation, and this equation we are numbering it as equation number 1. Now the conclusions that are drawn, that can be drawn from equation 1. From this equation, we can arrive at 3 important conclusions. The first conclusion, the total vapor pressure over the solution can be related to the mole fraction of any one of the component. That is, here you can see the total vapor pressure, it can be related to the mole fraction of any one of the component, either chi1 or chi2. Next, the total vapor pressure over the solution, it varies linearly with the mole fraction of the component 2. That is the total vapor pressure P total, it varies linearly with the mole fraction of component 2. That is, you can see this equation, P total is equal to P10 plus chi2 into P20 minus P10. That means P total depends on the mole fraction of component 2. That means as the mole fraction of component 2 increases, the P total value also increases. So that is the second conclusion, the total vapor pressure over the solution, it varies linearly with the mole fraction of component 2. Now the third conclusion, depending on the vapor pressures of the pure component 1 and 2, the total vapor pressure over the solution phase may increase or decrease with the increase in the mole fraction of the component 1. That is, see, with the depending on the value of the vapor pressure of the pure components, that is, pure vapor pressure of the pure component means P20 and P10. So depending upon the value of P20 and P10, the total vapor pressure can either increase or decrease, okay, with the increase in the mole fraction of the any one of the component. Okay, so these are the 3 important conclusions we are arriving at. Next, we will see the graphical representation, or we are going to see the plot between P1 or P2 versus mole fraction chi1 and chi2. Okay, so here in this vapor pressure in this plot P1 or P2 versus chi1 and chi2, we are taking vapor pressure on the y-axis and mole fraction along the x-axis. Okay, now, so we listen to this graph very carefully. Now, in this graph, we can see three lines. Can you see this? That is line 1, line 2 and line 3. Now, first I am going to explain this line 1. In this line 1, you have to see carefully. That is, see here, mole fraction, that is chi1. Okay, chi1 is in this, it is equal to 0 at this particular point. You please see the mouse pointer. Chi1 is equal to 0 here. And then as the value of chi1 is increasing in this direction. It is increasing in this direction. You can see the pointer. So it is increasing in this direction, and finally the value of chi1 is becoming, chi1 is equal to 1. So this is the direction in which the value of chi1 is increasing. Now we will see the plot. Now you can see that as the value of chi1 is increasing, that is as the mole fraction of component 1 is increasing, you can see line 1, the partial pressure is also increasing. It is slowly increasing as the chi1 value is increasing, P1 is also increasing, and finally when chi1 is equal to 1, that is when the mole fraction of the component 1 is equal to 1, the vapor pressure is nothing but it is the vapor pressure of the pure component, that is P10. That means at chi1, that is when mole fraction of component 1 is equal to unity, the partial pressure is the partial pressure of the pure component 1, that is P10. Okay, so this is the line 1, that is P1. Always you should remember, mole fraction varies linearly with partial pressure. As partial pressure increases, mole fraction increases, or as mole fraction increases, partial pressure also increases. So this is line 1. Next, moving on to line 2. Line 2 is a plot of P2 versus chi2. Line 1 is a plot of P1 versus chi1. Okay, line 2 is a plot of P2 versus chi2. Now here you should be very careful. That is, in this chi2, here chi2 is equal to 0 here. Okay, now and the chi2 value is increasing in this direction. Please see the mouse pointer in this direction. And then finally from chi2 is equal to 0, it is reaching chi2 is equal to 1. Okay, so in line 2, what is happening? As the value of chi2 is increasing, the partial pressure is also increasing. Partial pressure is also increasing. Now, when chi2 approaches unity, when the value of chi2 is equal to 1, that partial pressure is the partial pressure of the pure component 2, that is P20. So when chi1 is equal to 1, that partial pressure is P10, that is partial pressure of the pure component 1. When chi2 is equal to 1, this is P20, that is the partial pressure of the pure component 2. Okay, so this is now line 2. In line 2 also, partial pressure varies linearly with mole fraction. So this is line 2. Next, coming to, now we will explain the last line, that is line 3. Can you see the third line here? And this line is the line for P total. So P total, we already know from Dalton's law of partial pressure, we have learned P total is equal to P1 plus P2. That is the sum of the partial pressures of component 1 plus component 2, that is P total. Now, if you see this P total graph very carefully, you can see that this P total graph, or this P total, the third line P total, it varies linearly with the mole fraction of component 2, that is chi2. That is, as the value of chi2 is increasing, the P total value is also increasing. So the P total versus chi2 graph, it is a linear line, and this is line number 3. Okay, so P total versus chi2. Now in this line number 3, we should observe it carefully. We can see that in the P total value, the minimum value is P10 and the maximum value is P20. Okay, so minimum is P1 and P10 and maximum is P20. From this we can arrive at a very important conclusion. So maximum value is P20. What does it mean? Maximum value is P20 means, see, more amount of component 2 will escape into the vapor phase, or we can say that component 2 is more volatile. Component 2 is more volatile. That is why the vapor pressure of component 2 is high. Okay, so component 2 is highly volatile, whereas component 1 is less volatile. So we can say that P20 is greater than P10, or we can say that P10 is less than P20. So these are the important conclusions we can arrive at from this graphical representation. Next, we move on to the other concept, that is, if y1 and y2 are the mole fraction of the components 1 and 2 in the vapor phase. Okay, so in the vapor phase, if y1 and y2 are the mole fraction of components 1 and 2 in the vapor phase, then according to Dalton's law of partial pressure, we can write it like this. P1 is equal to y1 into P total, and P2 is equal to Y2 into P total. Here you should be very careful. Y1 is the mole fraction of the component 1 in the vapor phase, and Y2 is the mole fraction of the component in the component 2 in the vapor phase. So in general, we can write the relation like this. Pi is equal to Yi into P total. So this is another important relation. Next, we will see Raoult's law as a special case of Henry's law. So Raoult's law, it is a very special case of Henry's law. According to Raoult's law, the vapor pressure of the volatile component in the solution is given by. So this is the expression for Raoult's law. What is it? P1 is directly proportional to chi1, or P1 is equal to P10 into chi1. Now, according to Henry's law, we are expressing the solubility of a gas in a liquid. In Henry's law, it is given by P is equal to Kh into chi. So according to Raoult's law, partial pressure P1 is equal to P10 into chi1, and according to Henry's law, P is equal to Kh into chi. Now, if we compare these two equations, that is equation of Henry's law and Henry's law as well as Raoult's law, the partial pressure, we can see that partial pressure of the volatile component. In Henry's law, we are considering volatile component. Partial pressure of the volatile component as well as the partial pressure in Henry's law, we are considering the partial pressure of the gas. So, partial pressure of the volatile component or partial pressure of the gas in the Henry's law, it is directly proportional to the mole fraction. So, in both the equation, partial pressure is directly proportional to the mole fraction. So, only term that differs in these two equations is the proportionality constant, that is P10 and Kh. So, we can say that Raoult's law is a special case of, Raoult's law becomes a special case of Henry's law when Kh is equal to P10. When the Henry's law constant Kh becomes equal to P10, Raoult's law becomes a special case of Henry's law. So, this is the Raoult's law as a special case of Henry's law. Next, we move on to the next concept, that is vapor pressure. So far, we were discussing about vapor pressure of liquid solutions. Next, we are going to discuss about vapor pressure of solutions of solid in liquid. Now, we are going to dissolve a solid in a liquid. So, in that case, what is a vapor pressure? So, before going into that, first we should see this diagram. That time so you can understand it better. In a pure liquid, that is only we are taking a solvent, okay. So in a pure liquid or in a pure solvent, the entire surface is covered by the molecules of the liquid. The entire surface, it is covered by, you can see the blue spheres, you can see it is the entire surface is covered by the molecules of the liquid. Now we are going to add a non-volatile solute. Non-volatile solute is added to a volatile solvent. Okay. Now, non-volatile solute means that solute will not escape into the vapor phase. Okay. Only the solvent molecule. Solvent is volatile, so it will escape into the vapor phase. Okay. So, when a non-volatile solute is added to a volatile solvent, the vapor pressure of that solution, it is only due to the presence of the volatile solvent that is present in the solution. Now, the vapor pressure of that solution, once the non-volatile solute is added to the solvent, volatile solvent, the vapor pressure of the resulting solution at a given temperature, it is found to be lower than the vapor pressure of the pure solvent at the same temperature. Now, what will be the reason for this lower vapor pressure of the solution? The reason is that in the solution, the surface has both solute and solvent molecules. Therefore, the fraction of the surface covered by the solvent molecule get reduced, and hence the number of solvent molecules escaping into the vapor phase is reduced. Therefore, the vapor pressure of the solution decreases. So, more and more amount of the solvent molecule, it cannot escape into the vapor phase because on the surface of the solution we have the solute, non-volatile solute, as well as the solvent is there. So only very few number of solvent molecules can escape into the vapor phase. As a result, the vapor pressure is considerably reduced. So this is the vapor pressure of a solution of a solid in a liquid. Okay, so I hope this is clear for you.